Hello, 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 hello. सर एक बार चेक ऑन बोलिए सर. हेलो हेलो हेलो. ও তো এখন ঠিক হয়েছে তো. हेलो हेलो.
Hello,
Hello, hello,
hello, hello, hello, hello, hello. It's max, it's max, max, max already. The volume here, yeah, full. Hello, 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 hello. Okay, okay. Good morning, everyone, and welcome to the third day of the course. Today will be the lecture number 6, microfabrication, materials deposition. So today we will look into the materials deposition as we have gone through the general process and the of MEMS fabrication or microfabrication. We know that there are certain process that require deposition of thin films, and there are certain requirement for the device to have thin film to be deposited. For example, to have a circuit on the device itself, and to have a structural on the certain different materials in the device itself. Then we will look into how we can do the process and to deposit the materials, as well as to make into structure and useful circuit, for example. So we will look into the process of materials deposition today. So what we're going to look today is on the thermal oxidation, the basic process, some fundamentals, and physical vapor deposition, which is very common in MEMS fabrication, or we call it PVD. Then we have a chemical vapor deposition. What is it all about? Then finally, we look into electro deposition. So these are the process which are quite common in the process of MEM fabrication or microfabrication. So thermal oxidation, firstly, what is thermal oxidation? A method of foregrowing a film of silicon dioxide from a single crystal silicon wafer or a polysilicon thin films. So basically, as we discussed before, that in a MEMS device, we know that silicon is a semiconductor material. Then normally we will have a layer of non-conducting layer, which act as insulator. So silicon dioxide is an insulation materials, so that it can be deposited or grow on the silicon substrate easily with this kind of control with high temperature process, 700 to 1000 degrees Celsius. It depends on the process. We have a different process basically. Used extensively in commercial ICs, integrated circuits, and MEMS. And thermal oxidation by far is the most important method for growing silicon dioxide thin film, in contrast several other methods like PECVD and electrochemical process. So basically, we can have silicon dioxide through other process other than thermal oxidation, but thermal oxidation is the most kind of used process in order for us to obtain silicon dioxide, and it's a kind of the, maybe I can say, the easiest and cheapest method. One of the major reasons for the popularity of silicon ICs is the case with silicon forms an excellent oxide, SiO2, silicon dioxide. So we know that when you have some conducting circuit on top of the silicon, it needs to be isolated or prevent from contact with the silicon material substrate itself. So silicon dioxide is a very versatile, very good material and easy to fabricate in order to become the insulation materials. So why is it done? It's for, I keep mentioning this, for masking material. In the process of lithography, for example, it can act as a masking material. Mask meaning you want to cover something, and before you do etching for materials removal, for example, because silicon dioxide will prevent certain chemical from the reaction. And also for electrical isolation, as I mentioned before, and surface modification, and biocompatibility with a certain biomaterials, and thermal isolation, because silicon dioxide has different thermal properties, and sacrificial layer in the process of, let's say, lithography. We want to have a certain structure and certain process steps, then some steps it can be used silicon dioxide as sacrificial layer. So this is an example of MOSFET basically. So we have silicon dioxide here, and this is another silicon dioxide. Then, I mean, in terms of structure, it behaves differently. So this is as a dielectric material, silicon dioxide, and certain process is just to prevent, because you have polysilicon here. You want to isolate from, to have a structural interconnects with something. So here you want to have this, to not to connect with the some other parts. So you have dielectric, SiN, silicon nitride. Then you have aluminium. So these are things that you need to deposit basically. So you need to deposit silicon dioxide. You need to deposit polysilicon here. You need to deposit aluminium here. So the process will be varies. For us to deposit certain materials, you have a certain process, and aluminium you might use certain different process, etc. So this is, why materials deposition is very important in MEMS fabrication. As you can see here, we have a silicon substrate, then silicon dioxide. So in order for you to make this structure, you need to deposit maybe the whole surface, then you do the process. So here you have a polysilicon deposited. Then in this case, it acts as sacrificial layer. After you deposit silicon, you remove this silicon dioxide, then you get the cantilever of polysilicon. So this is act as sacrificial layer. And in this case, on the left-hand side, in this case, silicon dioxide use gate oxide, field oxide, etc. So it serves different purpose, but with the same material. So for silicon dioxide, the desired properties, the electrical, high breakdown strength. So it will be very good as insulator. So low amount of undesirable charges, interface trap charge, and mobile ion charges. And as for mechanical properties, no pinhole, and it's uniform thickness and density. So then we have these are the other physical property of silicon dioxide. Okay, we can see that it has a quite high melting point. If we produce with 1,700 basically degrees Celsius up to, and we have a refractive index of 1.46 and specific heat of 1, etc. So with a linear expansion coefficient of 5 times the 10 to the power of minus 7 basically, and thermal conductivity of 0.04. So these are a very good property in terms of the application in MEMS and IC device. So how does silicon dioxide produce? Dry oxidation. Through a process, dry oxidation, we have silicon solid, maybe silicon wafer. Then we flow oxygen, then you can grow silicon dioxide on the surface of the silicon wafer. So you can get through dry oxidation. And for wet oxidation, when we have a solid silicon, then we flow water vapor basically then we can get silicon dioxide as well. The silicon is consumed in the process because it's the reaction between silicon and oxygen to form silicon dioxide. So the interface produced by thermal oxidation, oxidization is not exposed to atmosphere, minimizing the impurities. Basically, we do it in a furnace. Then we get, if this is your silicon substrate, then we can get the silicon grow on the surface as a silicon dioxide. So these whole things you can calculate basically on how to get the thickness of silicon, how long you can expose to the process in order for you to get certain thickness. So structure of silicon dioxide basically is tetrahedral structure in this form. Then is in two-dimensional representation of, here is two-dimensional representation of crystalline structure of silicon dioxide in quartz crystal lattice. And here we show that in a two-dimensional representation of the amorphous structure of silicon dioxide. So in the process of thermal oxidization, since oxidization occurs at the silicon and silicon dioxide interface, so the O2 or H2O in vapor basically must diffuse through the previous grown oxide film. So you have the film, you have this semiconductor, material, the silicon. So it has to diffuse firstly diffuse at the first layer, then it will diffuse further in order for you to have a growth of silicon dioxide. So the oxidation or the growth rate will fall with time and oxide thickness. So the dynamic of the growth will be slower over time. The concentration of the oxidizing species, oxygen or water, at the air and silicon dioxide interface is a C0 here. Then Cs is the concentration of the oxidizing species at silicon dioxide and silicon interface. This is the beginning of the process. And F1 is the oxygen flux through the oxide layer, and F2 is the reaction. So the reaction towards the center of the silicon substrate. So F equal F1 equal F2 basically. So this is a kind of a reference for oxidation process. So oxide thickness, then you have oxidation time. So we can know that at what temperature, let's say at 900 degrees Celsius, so at 10 hour, you can get oxide thickness of about, let's see here, 0.1 micrometer. So this is for this is dry oxidation, and this is wet oxidation basically. So for wet, for 10 hours, you can get for this at thickness of 1 micrometer, almost the same time. Then if you see that the dry oxidation, you can go up to 0.8 here, 0.9. If you have a temperature of 1200 degrees Celsius for 10 hours, but here for wet oxidation, you can get 1 point, maybe here, not 1, this is 2, 3, 4, 4 micrometer for at 1250 at, for 10 hours of oxidation process. So in wet oxidation, you can get higher thickness in comparison with a dry oxidation process. So an oxidation furnace, an overview of this. Normally you have a resistant heater here. So this is the furnace and the heater covering the furnace. Then we flow whether oxygen or water vapor to the furnace, and you have your silicon wafer standing on a board. We call it a fused quartz board here. Then with a control of time and flow rate of 1 liter per minute, for example, then you can get the process done. If it's 5 hours or 10 hours, it depends on the required thickness of your silicon dioxide. So how you can measure the oxidation thickness? We can use a profilometer, meter, and color to differentiate the thickness that we obtain. I think this is quite common, then maybe I can skip. So next, we will look into the next material deposition, which are physical vapor deposition and chemical vapor deposition. So these two you might use for the deposition of metal, might use for organic and inorganic materials as well as the silicon dioxide, but with different intention. I mean, in comparison with silicon dioxide growth, when you grow using thermal process in comparison with this process. So what is physical deposition or PVD? Is a thermal evaporation. Is part of, can be considered as the PVD as well. We have sputtering and evaporation and sputtering in comparison. And then MBE, laser sputtering, ion plating, and cluster beam deposition. And then we will look into CVD, chemical vapor deposition, the reaction mechanisms, step coverage, and CVD overview. Then we'll see if we have time to cover epitaxy and electrochemical deposition. So what is a PVD? PVD is in PVD, chemical reactions are not involved except for reactive. Add reactive gases into chamber. We add some gas, but it's not as like in CVD. It's a really chemical reaction. But evaporation or a reactive sputter deposition, which are not widely used. So in evaporation, material source is heated to high temperature in vacuum, either by thermal or E-beam method. Basically, it's like that you heat up something until it's evaporate. So that is evaporation. And material is vapor transported to target in vacuum. Then film quality is often not as good as sputtered film. That is the comparison we're going to do later on, that involve energetic bombardment of ion to the as-deposited film, which make the film denser. So that is a quick comparison between evaporator and sputtering. The film thickness can be monitored precisely using a quartz balance. This is necessary as the deposition is not reproducible, and a tiny change in thermal leads to large change of deposition rate. T is not monitored. Power is, because in evaporation, basically we supply the current to the heater. So we control the power. It's not controlling the temperature. Where else the temperature is the main parameters that direct control of the evaporation, to evaporate the materials. So in order to control this, to monitor the thickness of the deposit material, we have to kind of have different way of monitoring it. So this is evaporation. This is a sputtering basically. So for sputter deposition, there is also a sputter etching. For the process itself, a material is removed from target by a momentum transfer. So basically, you have your gas, then the ion of this gas bombard to the target sputtering, then it will energize the molecule here, then you can deposit on the substrate. Okay, the gas molecule are ionized in a glow discharge or plasma. Ions strike target and remove mainly a neutral atom. Then sputtered atom condense on the substrate. So not in vacuum, argon pressure with 5 to 5 millitorr. And the detail of sputtering. Sputtering is process that atoms are rejected from a solid target material due to the bombardment of target. So you have the gas ions, so bombard to the target material. Target material normally in the case of metal, we deposit, let's say, chrome on the surface of a device to make it into electrical circuit. It can be aluminum, it can be titanium, it can be gold, for example, as the target material. So this will need a different control in order to have different materials to be deposited. So ion with energy less than 10 electron volt could also be absorbed to the surface, giving up the energy as heat. So it will heat up this material basically if it's less than 10 electron volt. Ion with energy above 5 kilo electron volt will penetrate into the material and transfer the energy to atoms in the target material. So the higher energy of the ion will be transferred to the atom of the target material. Ion with medium energy transfer part of energy to heat and use the other part of energy for physical rearrangement of the target surface. The atom of the target material will be ejected. So it's eject, and then you can deposit on your material. So there are two types of sputtering system. So one is called DC, one is called RF, direct current and radio frequency kind of powers for the sputtering. So DC sputtering used for sputtering metal materials such as aluminum, titanium, and gold. The target acts as the cathode in the diode system. So you have substrate wafer. So you have target here. So normally you want to sputter or deposit the materials on this substrate, on this wafer or substrate. Then you can change the target here. So RF sputtering used for dielectric materials such as silicon dioxide and alumina, basically. Using DC sputtering for dielectric material will cause the build-up of positive charge on the target. So that's why we use sputtering, RF sputtering. And we have talked about evaporation. This is a schematic of a chamber for evaporation. So it's a very simple kind of setup for evaporation. So the chamber is, this is a vacuum chamber. You have your boat here with heater. So the source material will be put here. Then you heat up this material until it's evaporate. So then you have your wafer or anything, any base substrate or materials you want to deposit the thin film of the target materials. So in evaporation, source material is heated in high vacuum chamber. which is 10 to the minus 5 torr, hence the name vacuum deposition. So high vacuum is required to minimize collision of source atom with a background species, and heating is done by resistive or E-beam. We will look into the E-beam evaporation as well. So surface interaction are physical, can be very fast, but film quality may suffer. So as mentioned before, evaporation might not give you the best quality of the thin film in comparison with sputtering. So evaporation is the most popular thin film deposition for nanofabrication using lift-off process, because in lift-off process, you want the deposited thin film to be a sacrificial layer, basically. So you want to lift off. So deposition rate is determined by emitted flux and by geometry of the source and wafer. And evaporation is not widely used by industry because sputter deposition is much better in terms of quality and control of thickness, etc. For microfabrication R&D, evaporation is as important sputter deposition, because in a vacuum is much easier in terms of setup, and it's much cheaper in comparison with a sputtering machine. So in evaporation process, when we heat up the source here, basically it will go directly to the wafer. It's just flow up to the substrate. So assume a particle of diameter sigma moving in speed of v here. So collision cross section is a pi sigma square. Collision volume swept during the time delta t equal a pi sigma square v dt. So the number of collision during the time is this equation. So here n divided by v is number of density. So we know that with this equation, we get the number of, the density is not that high when we compare with the speed if you use a sputtering machine. So assume sigma as 3 Armstrong, T is 300K. With this, you can have a power of 7.8, for example. So mean free path of the gases is varied, basically. So you have oxygen with this value at atmospheric, then we can adjust accordingly to what gas we are using. So I think this is less important. Let's say for different pressure, different vacuum pressure, then you have a different mean free path, and you have a kind of monolayers of that they can obtain. So deposition rate across a wafer. So you have a wafer substrate here. So this is the whole width of the substrate. Then you know which part will be thicker and which part will be thinner, because the mean free path of the evaporated material will be different, because the distance and the direct from here, from the bottom to the top, will be different mean paths. So this is another example, uniform isotropic emission from one point. So this will be, how you can get perhaps more homogeneous thickness. Okay. So evaporation characteristic of material. So you see that for aluminium, evaporation temperature is 1010 basically, and you can use the crucible, the boat of boron nitride, then deposition rate at 20 Armstrong per second, then the power of E-beam is 5 kilowatt. So this is kind of a reference if we want to do evaporation, then we can have this kind of setting in order to obtain certain thickness and to calculate a certain thickness. If you have different times, let's say this is 20 per second Armstrong, yeah. So evaporation characteristic. So for material such as let's say tin, so you can have a minimum evaporation temperature of 997, then deposition rate of 10 Armstrong per second, then power of 2. So this is another example of different material. So this is typical source of material for evaporation. So you can put in the crucible, then start to heating and until it's evaporate. And three types of evaporation according to heating method. So it's just the different heating method we classify the evaporation. So thermal evaporator, resistive heating, the only choice for evaporation of organic material. Then, as I mentioned before, there are electron beam evaporator, heated by electron beam, most popular, most expensive. Then thermal evaporator. Then we have inductive heating, which is not that widely used maybe. So this is it. For inductive heating. We have inductive coil in this crucible. Then it will heat up this material until it more and evaporate. Then you can have a deposition, as I mentioned before. So we go through quickly. Then this is another, setup of this evaporation of using inductive heating. So the common evaporation materials are metals. So this is a photo of evaporator. So you have this kind of bell jar shape. So inside you have this is your kind of your boat for heating. So this is inside the jar. The setup is very simple. To make, when you vacuum the jar and heat up the materials here, you put your wafer here, then you can deposit the materials. And this is for electron beam evaporation. It's just a matter of different heating method, but the process mechanism is the same. So you have your crucible, you heat up using filament of E-beam here, electron beam. So then you can have your material evaporated. So this is a kind of the setup of the E-beam. You put your crucible here, basically. Okay. And the difference between E-beam evaporation and thermal evaporation is that for the metal or low melt point materials, and for E-beam you can both have both metal and dielectric material, which normally have a higher temperature melting point. And typical evaporant, these are the material, everything above, and including this material. And for thermal is high impurity, but E-beam with a low impurity. So deposition rate higher for the E-beam, and temperature range is, of course, E-beam is higher, and the cost is high for E-beam. So, and the comparison, thermal evaporation is simpler in comparison with electron beam, robust and in widespread use. Use a tungsten molybdenum filament to heat evaporation source, and typical filament current are 200 to 300 amperes, and exposes substrate to visible or IR radiation. So in comparison, electron beam is more complex but extremely versatile. You can have many materials to be evaporated, and virtually and any materials, basically up to 3,000 of heating. And less contamination, less heating to wafer, and exposes substrate to secondary electron radiation, and X-ray can also be generated by high voltage E-beam. So these are containers for evaporator and resistor, just to share some parts of the process. And for the crucible, you have tungsten, tantalum. Accordingly, you can use, if you have a higher temperature material, you can have tungsten, for example, up to 3,380. And if you have a graphite, you can go higher, 3,700, for example, and so on and so forth. So this is what we call as the quartz crystal microbalance, or QCM, in order for you to monitor the thickness of deposited film. So how it works? Quartz is a piezoelectric material, basically. So with a high frequency AC voltage activation, the amplitude of vibration is maximum at resonant frequency. Then this resonant frequency will shift when film is deposited on the surface. When the thickness change, the frequency will shift. So that's where you start to detect the thickness of the film deposited. Thus, by measuring frequency shift, the delta F, one can measure film thickness with a sub-Armstrong accuracy. So the issue with evaporator, we have seen that it will go straight. Basically, if you want to have evaporation, material. So if you have this kind of structure, so you might not be able to, in some cases, it will have this kind of issue. It's not covered. It's not, deposited on certain area. So step coverage is poor because of this kind of shape. So basically, you don't want to have a too high aspect ratio of this, and maybe the step should not be in this way, but a little bit open, for example, instead of straight. So heating can decrease SC, but may change film properties. So you keep deposited, then you can get this kind of deposited thickness. So it will grow low at atom mobility and non-rotated. So then, therefore, due to poor step coverage and X-ray damage rarely used in IC fabrication. So here, final profile of the deposited, sometimes it can become like this because, at the wall, the rate of materials evaporated is the same. At the same pathway, then this pathway is kind of deposited here, but of course, this is the whole pathway of the evaporated material is just to be covered in this narrow section. So that is why you cannot have a kind of same film thickness at the wall of this trench. So, and the depositing, if you change a little bit, then let's say you rotate or you have some angle of the materials to be deposited, then the depositing species has a high SC, so they are deposited where they first strike. So the depositing species have a low SC, so many are re-emitted and redeposited as well, are not topography such as the sidewall. So, and for the stoichiometrical problem of evaporation, compound material, if you want to have alloy to be deposited, normally we deposited single material, let's say iron, gold, nickel, etc. But in case you want to have alloy, then we might use two different materials to form an alloy. But in this case, you can see that the problem is with a shadow problem, that you might not be able to have a good deposition of alloy if you have two different sources. So another issue is the glancing angle deposition, self-assembly of thin film. We try to have this kind of angle more than 80 degree without substrate rotation. So you have your substrate, so you have a slanted columnar film microstructure here. Then you try to deposit something in this kind of angle. So you have a vapor source here, then you have the incident, then you can kind of deposit on the substrate at the angle. So this is an example. So it can, I mean, this is in terms of the straight deposition for the substrate. If you make an angle, you can have this kind of crystal or structural deposition, I mean, accordingly. And this is showing the various types of clad. If you try to deposit with certain parameters that can be controlled. So in summary, for evaporation, so film can be deposited at high rates, for example, 1 micrometer per minute, though for research typically 0.1 micron per minute. So it's a low energy atoms leave little surface damage. It's not a bombardment of atom, little residual gas and impurity in compression due to high vacuum conditions, and no or very little substrate heating. And next, we will look into chemical vapor deposition. So you have covered PVD. Now we look into CVD. What is CVD? CVD is a chemical vapor deposition used to create high quality thin solid film and coatings on a heated substrate through chemical reaction or gaseous precursor at high temperature. So this is a schematic layout of a CVD, typical schematic layout. You have precursor flowing into the chamber, the furnace basically. So diffusion happen, then gas phase reaction happen, then with that you can deposit material on the surface absorption, and material can be grow on the surface of your substrate. So CVD allow precise control over thin film properties and the coating of complex shapes, making it crucial for application in the semiconductor industry, aerospace, for example, turbine blades, and the synthesis of advanced material like carbon nanotubes and graphene. So it's more towards the different types of material deposition. So CVD process introduce reactive gases to the chamber. So you have reactive gases, hydrocarbon gas, and inert gas coming in. Then thermal decomposition of the gases through heat or plasma happen inside. Then gas absorption by substrate surface. You have your substrate here. Okay, the substrate. Then with a certain catalyst, basically, it depends on the process of the growing what types of material. So reaction take place on substrate surface and thin film is firm. And transport of volatile byproducts away from the substrate. This is the outlet gas. So basically, you can grow CNT, carbon nanotubes, or even the material such as I mentioned before. And you can also grow silicon on the substrate as well, polysilicon. So the physics and chemistry involved, dilution of SiH4, basically, the silane gas, the decomposition of silane, the precursor around the susceptor decrease the deposition rate and concentration of silane along the length of the reactor. So we have the reactor in this manner, right? The gas come from here, but towards the end of this chamber, the gas become less dense due to reaction. Concentration will be less. So the surface will have concentration of vacancies brought by H2. So homogeneous and heterogeneous reaction. Homogeneous meaning atoms of the solid are released from the gas, and heterogeneous atom of the solid form of the wafer substrate, which is more preferable. So this is the other material, basically, if you want to have the happen in the CVD chamber. So the reaction happen, and for the gas flow determines the transport of the various chemical species in the chamber as well. And the temperature effect is very important to control the deposition rate, uniformity of the film deposited, and hot wall batch CVD reactor, for example, for large batch processes, excellent temperature control but low deposition rate. So there are three types in general. There are more than this, but this is the most common types of a CVD using various techniques. What we call as APCVD, which is done at atmospheric pressure, and LPCVD, low pressure, and then we have a PECVD, which is a plasma enhanced CVD. So all these have their own advantage. For example, APCVD is simple and fast, and LPCVD, excellent cleanness and conformity and uniformity, and PECVD at low temperature. So disadvantage plus step coverage is like something similar with an evaporator. And for LPCVD, high temperature, low deposition rate, can have high deposition rate as well. But rise for particle and chemical contamination in PECVD. So, but as for pressure and temperature here, atmospheric pressure with a temperature 300 to 350 to 1,200 degrees Celsius, then low pressure at 100 Pascal, and temperature of 550 to 600 degrees Celsius. And for PECVD, plasma, 200 to 600 Pascal, and the temperature of 300 to 400 degrees Celsius. So this is a typical setup of APCVD. As you can see here, we have gas, etc., and the heater. So it's quite a simple setup. And this is LPCVD. So you have heated here, and you have shower and gas inlet here in order to deposit the materials. You have different arrangement as well. This is LPCVD, and this is a kind of PECVD setup layout. So with different setup, different arrangement of the CVD, you can have different quality of the deposit film. And another CVD is what is called MOCVD, metal organic CVD. And the advantage of this metal organic is highly flexible, can deposit semiconductors, metals, dielectric, but the disadvantage is highly toxic, very expensive source material, and environmental disposal. So the cost is high. Users dominates low cost capital, but not electronic, 3-5 technology, and some metallization. So these are the comparison of this CVD process for with APCVD have the advantage of high growth rate at atmospheric pressure, and LPCVD low pressure, high purity, and PECVD low temperature, good for filling small features, and MOCVD flexible with the materials. And we can see the rest of the advantage and disadvantage of this system. So next we will look into epitaxy. What is epitaxy? Epitaxy is deposition of crystalline overlayer on a crystalline substrate. Basically, we try to deposit layer by layer of material. So requirement, the substrate must act as seed crystal, which preferred crystal orientation. So the thing is, the layer need to have a seed. So application to deposit a single crystal silicon, for example, 30 to 100 micrometer, compound semiconductors and semiconductors heterojunctions. So epitaxy method, we have two types, vapor phase epitaxy, very common, and MBE, molecular beam epitaxy. So the process start with wafer cleaning as normal, then with RCA cleaning, then you do the epitaxy growth. So this is for MBE. The crystalline layer is formed, and you have your substrate of seed, then you form the layer on the substrate. So the crystalline layer is formed by deposition from a thermal beam of atoms or molecule. Deposition is performed in ultra-high vacuum condition. So 10 to the power of minus 10 torr, and the substrate temperature is 400 to 900 degrees Celsius. So in terms of application, growth thickness with atomic resolution. So it's a very thin and precise layer can be deposited, and good growth quality for semiconductor heterostructures. So next is on the electrodeposition process. So electrodeposition is quite simple setup. It's a quite cheap setup, I would say, because here you can see the layout of the setup. We need a cathode and anode. Then we apply potential or current density. Then you have your solution here or electrolyte. So with this kind of setup, for example, you can have some at the cathode to deposit. This anode is the base material. Then you have solution of SO hydro sulfuric basically. So then you can deposit copper on this cathode. So an electrochemical reaction, or sometimes we call it electroplating, or it depends. Cathode is a metal or alloy coatings, and anode is soluble or insoluble material as well, and conducts different solution with the ionic species, and transfer of electron happen to the materials. So this is the actual setup of a copper anode and steel cathode, and you have your power supply. The reaction happen is Cu2 plus 2 electron. Then you can get copper. So from here, you can see that it's deposited on the this is the cathode. So the reaction happen at the cathode. So electrodeposition of copper, as mentioned before, Cu2 plus 2 electron, then you can get a copper, bulk copper substrate. So at the same time, hydrogen evolution happen, 2H plus 2 electron, then you can get the hydrogen gas release. So at the anode, the soluble anode, Cu minus 2 electron basically, then you get 2 Cu2 plus. Then insoluble anode, you have H2O minus 2 electron, you get 2H plus 0.5 oxygen. So the overall reaction is this manner. So you have the bath, what we call as the bath here, or electrolyte. So provides an electrolyte basically for the bath to conduct electricity ionically, and provide a source of the metal to be plated. So sometimes we dissolve the material, the salt, the material salt is as dissolved metal salt, leading to metal ions, and allow the anode reaction to take place, usually metal dissolution or oxygen evolution, and wets the cathode workpiece, allowing good addition to take place and help to stabilize temperature. And the thing is, in this case, if you want to deposit something on the silicon substrate, we need to have a conducting material on the top of the silicon substrate itself. So that is kind of a preparation that need to be done. The ion, typically what is in the bath, for example, what's nickel, we need nickel ions added mostly as sulfate. So the conductive electrode, nickel sulfuric, boric acid, nickel chloride, then nickel anode dissolution promoter, then pH buffer, boric acid, then we have additive wetters. Additive meaning something that you can enhance the process or try to improve the electrodeposition, or to speed up the deposition, etc., or to make the electrodeposition surface become homogeneous, etc. So that where we put the additive accordingly. In summary, electrodeposition is a coating, good coating technique, there is a high degree of control over deposit thickness, and many metals can be electroplated from aqueous bath, basically. So can some alloy conductive polymers and composite. So here, if you see that conductive is the keyword here, you need to have a conducting surface. Rate of electroplating can be expressed via Faraday's law of electrolysis. So basically, we can calculate in advance of the current density we use in terms of how it can deposit at what rate. So I think that's all. Thank you. Any question from the floor? If you have any question, yeah. Yes.
Vacuum is related to the quality of the product.
Pardon?
For PVD.
Yeah.
For PVD is the vacuum now.
The vacuum?
Vacuum is placed in the vacuum chamber.
Yes.
Is vacuum related to the quality of the material?
Yes, at a certain extent. That is why you see in evaporation, so it's less vacuum in comparison with sputtering. So at a certain extent, evaporation has more contaminant. I mean, not that good quality purity in terms of purity.
Contamination deposition.
Yes, because of contamination, because you don't really purge the chamber into vacuum, because with less vacuum, you are aware that there is some other materials, I mean gases inside.
And also in the last session, you tell that about conductive polymers.
Yes.
What any examples are related to conductive polymers? Because I am working on nylon.
Okay. So conducting polymers, meaning you have kind of make it into composite where you introduce some nanoparticle to make it conducting, right?
Okay, like that.
So let's say you embed graphene in the matrix, so it's become conducting polymers. Yeah.
Okay, sir. Thank you. Thank you. Thank you, sir.
So good morning, sir.
Yeah.
In this, while gas affects in CVD process, gas affect the material.
Yes. Because
like there's any chemical changes like that while heat treatment.
Yeah, CVD is basically chemical reaction happen with the precursor gas, so with the material. So, sorry, what's your, question again? Yeah.
In CVD process, you mentioned, sir. In that, we are adding gases.
Yes.
To remove
precursor. Yes.
To deposit material.
To react with the material to deposit. Yeah.
Because of the gases, there is any chemical changes in material depositing in powder.
The precursor meaning is a carrier. So when you say precursor, a gas is a carrier. So basically, the gas will be purged out, and the reaction, of course, the reaction will happen. The reaction happen inside the diffusion, for example, happen inside, and the reaction with the gas happen. Then the material, what you want to deposit, basically, you mean it will change in terms of the property of the material, right?
Yes,
it might have slight changes, but it's not significant. Normally, we consider it as pure as the film or the materials that we have. You want to deposit as, let's say we want to deposit gold, is still a pure gold. Yeah.
Thank you, sir.
Sir, also this gas flow now.
Yeah.
Gas flow, we are of laminar and turbulent.
Okay. The flow rate is very, very slow. Is it? I think 1 liter per minute, right? It's very slow. Just to fill, it's not just like well, I don't think it will create laminar flow or turbulent flow. I mean, it can be. It's just laminar flow. It's not going to create turbulent flow inside. A steady flow because it's very slow, 1 liter per minute of flow rate.
Thank you very much, sir.
But the thing is, the issue is towards the end here. So the concentration will be less normally. So you have some not non-homogeneous deposition towards the end of the chamber.
Okay, thank you, sir.
Okay, if no more question, thank you very much. Then we shall continue with the next lecture. Thank you.